in a standalone mode, you can break these 40 gig ports to 4 10 gigs, so straightforward. Maximum throughput, you are getting 2.88 terabytes full duplex on these fabric connectivity. Layer 2, layer 3, both full line rate, because even in T2 you can support both modes. Support breakout, which we talked about earlier. The reason of the breakout is when we talk to a lot of customers, they actually using servers as a standard for 10 gig because they have Intel LOM ports. So they're saying, oh, if you give me 40 gig port, I'm not going to connect directly to 40 gig, right? I will use network to network 40, but I will use server with 10 gig. So we said, okay, we'll give you a breakout option. You connect a 40 on this port, and you break into 4 10 gigs, so you can have 4 different servers or chassis connected to it as well. So that was the reason we went to the breakout option. The same line card used in 4 slot, 8 slot, both. So you can reuse it. If you have 2 different types of chassis within your environment, you can consume it easily. So this shows the wiring diagrams or wire rate diagrams, how it's done. So you can see in a chipset, the Brydon Trident 2 chipsets, how they are done. You have 6 on each areas. So that combines you total 24 ports of chipsets. But it's maximum supporting 32 ports. So each LOMs connections, you will have 2 ports start and end that's not used with the chipset. So that's why 24 ports of ASIC supporting 32 ports. So you can have full line rate, that's how. And the full line rate will be maximum 24 because where the packets are entering to the chipset, it will do in and out. So that's where you get. So maximum you can get 24 full line rate packet, not the 32. So that's what you have to remember in 9600. And now how is done on 9600 from the diagram perspective. So if you look there, so these are the, again, NFVs are used for the T2, is a merchant silicon chipsets. So NFV, when it gets, so these are the front panel ports. So when it connects to the fabric module, you can see the fabric module will have 1242 gigs ports connecting to the fabric module, which is on the back of the chassis, and the front panel port will connect to the 40 gig ports. So this is how it will use from the line cards perspective. So maximum it will use 3 NFV ASICs on per line card that it's going to use. If you're using full 6 fabric modules, how it connects? So full 6 modules, each ASICs will interconnect to each of the 2 ASICs. So if you remember, this is one 9600 line card, and these are one fabric module. So I've done all the 6 fabric modules connected on the back of the chassis. So the pin outs will go that it will have 6 connections from here. So it takes 2 to each. So it's actually it's 12 connections total. So you will see 2 ASICs. So each fabric module has 2. So 8 connections to the one NFV. So 12 each is 36 connections per line card on 9600. So all of this port can give you the full line rate because it has full 6 fabric modules. It has 12 40 gig connections to the NFVs, and it gives you the full 40 gig bandwidth because of the 42 gig line card bus rate interconnections. So we did a lot of testing to show different variations of a combination of packets. So in this case, we did full line rate for 40 gig testing, where we learned that if we are doing full precedence line rate for testing for RFC 2544 and 2889 for different size of packets, here we are seeing sending and receiving performance of full. So you can see that unicast traffic and multicast has no impact on the performance. You can get 100% line rate on it. And we did for different packet sizes, that if we increase the packet sizes, we getting the full throttle still. So this shows you the real performance. And some of these performance numbers are published already on Cisco website, so you can reuse it easily. Same thing we did for latency, because sometimes, especially in the data centers, you have different types of combination of applications. You want to make sure that you have enough latencies and buffering done. So we did similar testing for it. We again use the standard RFCs to do the testing. So you can get with 64 byte packet size, 1.6 microseconds. Generally what we learned is it's a combination of different packet size. So if you're using virtualization, you will have a lot of jumbo frames as well. But if you have legacy, you will have 64 bytes or jumbo frames mixed combination. So even if you look in the jumbo frame, it will have 3.5 microseconds latency on the packet size. So these are some good tests that we did. Now then second line card comes up in the picture, which is ACI ready, 9500 series. So in 9500 series, the good thing what we did is that we are using 48 port dedicatedly for 1/10 gig. So either if you have 1 gig port or you have 10 gig port, it will auto detect for you. So as long as the cable supports, it will go and auto detect for you, either SFP or the copper, doesn't matter to you. But at the end, there are 4 port QSFP connections. So this QSFP plus, exactly what it does, the same thing that you did in 9600, you can break out as well in a standalone mode. So that gives you much more power to, let's say there's blade chassis connected, so you want to make sure that you get blade chassis connected for 40 gig, you can use that, or you can break out for 10 gig as well. So it gives you both options from fiber and copper as well, 1.2 terabytes fabric connectivity. Again, since we are using Broadcom and NCMA 6, we can do the same L2, L3 line rate performance on the packet sizes. It's both mode supported, standalone, which is Nexus OS, or ACI mode as well. Same line card can be used for all different slots, 4, 8, and 6. So how it connects within the fabric. So you can see it has less number of ASICs, right? So previously we were using 3 chipsets on 9600s for Trident 2. Now what we did is we took 1 off, but we added 2 of ours because we want to make sure that we are getting merchant Silicon's benefit on top of our stuff. So 2 is Trident 2 chipsets, then we have 2 our chipsets as well, which is ALE. So this, in this case, what happens when we added 2 of this, we can get additional buffering and additional packet processing power. This actually gives us a much more leeway with VXLAN routing, because when VXLAN routing comes in the picture, you want to recirculate the packet and you want to see the headers for forwarding purposes. And we'll see in the details in next couple of slides. So how it connects with the overall pictures of the fabric, right? So it has 2 Trident 2 chipset and then 2 ALE connects to the fabric, and then these are the front panel ports that's going to connect. So here you will see what NFV ASICs, which are T2 ASICs, are doing. It's using only for forwarding the engines for standalone mode. So packet comes in from the front panel port, which is this. It processes the packets and forwards it. If you need additional packet processing, let's say you have VXLAN header for routing, or you want to make sure there's enough buffering because there's a load is coming in, enough buffering, it will queue it here. So that's how we did a combination of both. And even it's in ACI mode, it will have policy supported here. So in ACI mode, what will happen? You will have regular L2, L3 packet forwarding at the front panel port, which is in NFV, but you will have a policy stored on ALE itself, because you want to make sure that policy routing should be done with the ALE chipset. So that's how we use this combination. So again, minimum 3 fabric modules can be used for bringing it up. So ALE, in this case, you see that T2 is not connecting with T2. ALE is connecting with the T2 chipset or Trident 2 chipset from Broadcom. But you're getting much more flexibility. You're using 2 links, 42 gig ports. That's how you get the benefit. So in full redundancy, yes, you can have all 6 as well. So if you're fully loaded chassis and you're doing full packet throttle, yes, you can do all the 6 stuff as well. Now this is a different line card where every port is 40 gig. So when we were working with customers, they said, okay, I need 1/10 gig both, because I might have legacy, which is 1 gig, and I have 10 gig also. But in future, they want to make sure that I have full 40 gig throttle or full 100 gig throttle. So 40 gig we already announced, 100 gig we are working. So here you can see 36 40 gig ports, all QSFP. It gives you 1.5 to 1 oversubscription ratio, similar throughput, 1.92 terabytes, because we are using the same chipsets. Here, if it's standalone, not in ACI, you have to remember, in a standalone you can do breakout. So in a standalone you can do 4 into 10 gig ports. So each 40 gig can be breakout into 4 10 gigs. So you have a lot of number of 10 gig ports. And again, it supports ACI ready from the chipset perspective. So how it connects, similar thing. It has ALE connecting to the fabric modules, front panel connecting to the Trident chipsets, minimum 3 fabric modules needed. So even we are increasing the bandwidth or the port speed, but you are not changing the requirement of the fabric module. So that gives you much more leeway. You can reuse from investment production the same modules. So now we'll go in the packet forwarding, which is much interesting. So how this packet forwarding really works. So first what we did is, since we are using a lot of Trident 2 chipset, we have to reuse what Broadcom Trident 2 chipset SDKs are giving us, because we cannot change that, right? Because packet, you have to understand that when packet enters the front panel port, it will hit the Broadcom chipset, and we'll use whatever the Broadcom SDKs are giving. Then we can add in top of it, right? So what we did here, the Broadcom chipsets come with a lot of different things. So they have almost 10 banks in the memory. So each bank has different logic, right? So bank 0 and bank 1 combines for L2 MAC entries only. Bank 2 to bank 5 used for shared entries. So if there are shared routes, you can use for there. And bank 6 to bank 9 are dedicated for L3 routes entries. And then they have a combination of different modes. So what they call is these modes can be used for different combinations. So generally recommendation is you use one mode versus other mode, right? You cannot use a mixed mode combination. So what we started, we focus more on mode 3 and mode 4, right? So in default setting 9300, we use mode 3 by default. But you can use even mode 4 as well. That actually gives us much more value, because here you will see that if there are more number of L3 routes, you are getting 128 routes. 128K is enough for a data center, because you're not getting whole internet route in that case. So that's how we focus on that 2 modes. So it gives us both options. So even L2 routes, you're not losing a lot. You have 96K, which is enough, because you are just doing MAC forwarding in that case. Or if you go mode 4, you're getting LPM, which is least packet match based on the host routes. So either you do basic L2, L3, you use mode 3, or if you want to do least packet match based on prefixes, you can do mode 4. So we have both combinations, and you can change with the command, so it's not much difference. So how packet really goes in the hardware level. So when packet enters, it enters from the front panel. It goes through a parser where the packet process happens. So real lookup will happen on the L2 and the parser, right? So parser will tell you, okay, this is a packet, this is header. Let's examine the headers and let's start processing it. When the processing happens, what exactly it looks? 5 tuple, right? Destination mode or destination port. Based on this, I will forward the packet. And once it does, the fabric module is where it will say, okay, if I'm coming from line card 1, I have to go to line card 3, because entry and exit might be too different. So based on that, it will decide which line card it has to send, and when it figures it out, it uses additional buffer if it's needed, and based on that port speed mismatch or whatever it has, it will send out to the egress line card, and that's how packet will get out. Pretty simple. Any questions on this? This will actually help more in the troubleshooting, because when you're trying to make sure, generally TAC uses heavily because they want to make sure that, okay, where this packet is getting dropped, or if there's a bug, how to figure it out. So the second option is how you do for L3, because again, we talked about different modes. As soon as you change the mode, the packet walk becomes a little bit different. So in L3, what happens, same thing, the packet enters to the front panel. Then you will do L2, L3 lookup. In this, since mode is changed to L3, it will focus more on L3. And then same thing will happen in the fabric module. Fabric module will just look for which line card it needs to send. If there's a buffer needed, it will add the buffers and the port speed, and then exit it out. So that's similar from the forwarding perspective. The only difference is here, the L2, L3 lookup will only look up for L3 packets. Now the unicast packet. So generally in networking, we have unicast packet working a little bit different from the multicast packet, because one is a spray and one is focused, right? So we will do it a little bit different. So what exactly we do in the unicast, the packet enters the same way from the front panel port. North Star or ALE doesn't get involved. So we are not even using at all in this case in SEM A6. So packet will be looked by the L2, L3 lookup. Fabric will use the mode ID to find out where its virtually internal header is located. When it figures out, the fabric module does the L3 portion in this case. So it does look for L3 LPM, which is a least packet match based on the route entries. And then it will send for switching to which line card egress it needs to go. And based on again, for the buffer and the port speed, it will send out to egress. So unicast will be looked a little bit specific because you want to know that these are the specific hosts match, and based on that it will go out. Now, the important thing is buffer allocation. So as we talked about that in CMA ASIC, we added a lot of buffer and capability for speeds and stuff. So what exactly we did? So here you can see when you use merchant Trident 2 Plus, right, we use 12 meg shared memory for buffer. It uses for both for front panel as well as for uplinks for the ALE as well. So this is a shared buffer use. But in the CMA ASIC, which is the ALE, you have much more flexibility. You have additional 20 meg as well as 10 meg for the buffer. So by default, if 9564 copper ports are using, you get 104 meg. So you are getting more buffer with additional 2 ALE engines. So you can see there, any 9500, you are easily getting 104 extra buffers. But if you use the merchant silicon, you will only get 12 meg buffer maximum. So that's what it gives you much more leeway for, especially for special applications where you want to do different sizes of the packet or different buffers for incoming and outgoing. It gives you much more confidence for packet processing, as well as the packet drop rate happens less. So that's what our focus was, to give you much more buffering options. Now, how this buffer boost will help, because what we are also trying it, we are giving you buffer option. At the same time, we want to make sure if there's buffer happen at a different rate, the buffer boost function, which is only in CMA ASIC or ALE, it will allow you much more additional buffer to be consumed, especially for 40 gig and 100 gig, where line rates are increasing big from the incoming packet, right? So buffer boost really by default is disabled on the ports because we don't want to enable for every packet for the buffer boost. So local traffic will always use within the NFV, which is your Trident 2 chipset, and it directly utilizes the NFV egress queue mechanism ports, so which is your front panel ports. And then buffer boost, when it is enabled, it will send the packet from the front panel chipset of NFV to ALE, and ALE knows that it's coming for boost, so it will use additional buffer by default, which is allocated for this purposes. And it gives you much more option, because not every packet will go to fabric module in this case. Because let's say I have a packet coming in for line card 1, and I already know I want to do buffer boost, but it doesn't need to get out of destination port to line card 3. It might be only line card 1, port number 40, right? So I can reuse NFV buffer boost and get out from there. So it actually it gives you much more leeway even for forwarding as well. So this is a very unique idea. When we were doing this design of the chipset, we learned based on different application requirements. So we focus on this buffer boost mechanism. This goes much more depth on the system QoS level. So in queuing, there are multiple different options, right? So if you look at the line card, this is the Trident 2 chipset, the NFV. This is the ingress line card, comes up with a lot of different mechanisms. So by default, we keep the marking preserved. We don't want to remark, because what we learned is in data center, QoS needs to get what is getting in and needs to get out what it wants to. You don't want to remark unless there's a lot of different sizes of QoS. So system queues are marked on at the fabric module level. So if you see here, the system queues are here at the fabric modules. So fabric modules, when they connect to the ingress line card, so it will do at the ingress level, and when it exits out, it will do itself. So fabric module, which has already the Trident 2 chipset, it will do that at that level. We don't want to use the line card for packet processing as well as the QoS, because then it adds much more overhead also on the top of it. So that's how we want to focus on the QoS stuff. Now, in this case, where we are doing the queuing with 9500s, we want to make sure we does the same thing, but at the same time, if there are hairpin traffic, because there might be case where packet is coming here and they're getting hairpin and then getting out. So we will only use, in this case, the ALE engine, because we already have a buffer. So why don't we use the buffer with the queuing option? So that's why you will see the packet won't go all the way to the fabric. It will just use the same mechanism we use for buffer boost option as well. So a similar thing we'll use for QoS. Now we have different options of queuing mechanism, right? So ingress QoS has a lot of different options, like you can do policy maps, you can do match on cost, IP precedence, you can use set QoS groups as well. or you can use network QS like policy options or PFCs, or you can do egress queuing like RED and an ECN mechanism. So there are a lot of different options. By default, Vue doesn't want to change the queuing mechanism. In standalone, you can do customization if you like, but at ACI, we don't recommend. The reason is because the way ACI is doing it has policy itself assigned to it. So if you're doing a policy, the policy will know that which packet needs to get which forwarding engines, and it has all the taggings itself. So we don't recommend to do too much changes on itself, and you already have the class bits defined on the policies itself. So standalone, yes, you can do whatever queuing you want to do, but in ACI it's much easier because in egress it will do everything as marked and will carry over. Now, the common things comes up, what are the default forwarding? So in 6.12 release, what we did is we set up the default, right? So we talked about the default that we're using 128K mode for L3 routes. For fabric modules, IP hosts are 88K routes, and MAC entries are 160, and multicasts are 32K. Hardware is capable of 72, but we are using. So generally what happens, what does really mean? When we deploy the first time, we want to test based on what customers are asking as a benchmark, because you don't want to utilize full, because if you use full, then some of the parameters are also interdependent on other stuff. So that's why we started with 32K, and we learned actually, this is actually interesting because I was talking to a lot of financial customers, especially on the trading floors. They are saying their maximum use 12K multicast routes averagely, because they distribute also their routes. So 32 we thought is a good enough number. Any one of you is thinking more than that, because maybe that will be a good idea to get feedback. Good. Then we are talking about different forwarding tables. So similar numbers on this, on the forwarding as well. Now, we have hierarchical modes, right? So we talked about standalone modes that has different other options. So what happens in the non-hierarchical mode? So if there's no forwarding, just basic L2 switching. So if line cards are programmed only for IP v4 LPM and L2 stuff, the numbers change a little bit. So here you can see it gives you a delta. The numbers are a little bit changed on this. So if you're using default, you don't need to worry because it will do based on L3 specific. But if you are changing, then you need to remember how these routes are. By default, our recommendation is if you have specific routes, you plan these routes, how you're going to mode it. Because if you're changing on one line card versus the other line card, you have to have a mix of both. So you do your programming around it. But by default, it will help you in. So maximum host mode. So this is actually a very interesting topic, right? So if you are using max host for IP host connectivity, especially this is for more for shared services, like you're doing storage or you are connecting large number of backup devices where you have large number of IPv4 or IPv6 dual stack modes connected. Here the numbers a little bit different because IPv4 we can do 16K, IPv6 we can do 4K. So if you're using dual stack on the same line card, you just need to understand that how these routes changes the calculation itself. How many of you are planning to use IPv4, IPv6 dual in the Nexus 9K? Any idea? Okay, good. Yeah, because we learned most of the folks are just using regular IP native v6 or IPv4 native. Good. So this shows the full system scalability. Actually, we found a lot of customers asking for, okay, give me a scalability guide. So what we thought, okay, maybe give you a table which has all the numbers itself. So this shows the full detailed of different modes of the line card and different values of each mode. So actually that gives you an option as a chart that if you are hitting which numbers, so which mode you should do. So it actually helps you in a design planning that if what numbers and what parameters you want to use, so you can plan on which mode you want to use. Does it really help this chart? Because Mike actually spent a lot of time on this to build this chart because we want to give to our customers so they can reuse it. Any questions so far? Good. So now we'll go on the fix slot. So far we talked about the modular stuff, which is 9500. Fix is 9300. So in 9300, the goal is similar. What we did is we have the front panel port is all Trident 2 chipsets, and the GEM modules are the ALE or NCM A6. So what we are looking is when we were designing this, we saw the higher speed improves ECMP efficiencies. So when we are looking, okay, we can have more ECMPs across the different ports, or what we can do is we can have ECMP to a specific gem module. So there were two different options that we can do. We found out the probability of 100% throughput relies if we do minimum number of ECMP links from a gem module. So that's how we designed 9300 fixed modules. Then we did a lot of different tests, because generally when we do, the idea is you talk to researchers, you do some simulation based on results, then you design, because you don't want to design and then do reverse engineering. So when we started, we talked to a lot of PhD candidates from Stanford, and what we learned is if you're using large buffer in the chassis with the different numbers of load, you can see the patterns are different. You're getting the buffers at the same time the load increases, your throughput changes as well. So this is how we learned the different pattern mechanisms of different sizes. So when we designed the fixed chassis, we designed according to this. So we have two different modules right now. So we have 9326 PQ and 93128TX. So PQ is more for the fibers, right? So you can have SFP ports connected here. So you can see all the front panels are SFP ports. And 96TX, as it says, TX is more for copper. So you have 96 ports copper. These are the gem modules that has ALE ASICs itself. So it talks about here, these are uplinks. So standalone, what you do is you use these for uplink, but in ACI, you have no option to connect anything on these gem modules. So you have to remember that which mode you're using it. So because in ACI, you cannot connect anything on these ports other than the spine itself. So that's the design thing that you have to always remember, because these ALE connects to the spine line cards as an uplink. So there are a bunch of different things. 9396 is coming soon. So there are 2 RU. Actually, there are a couple of things that we didn't show here. There's 1 RU also launched in Milan that we did. I think Mike didn't add it here, but we also added a fixed module for 1 RU, because a lot of customers were asking, can I have less space but similar number of ports? So we added that as well. So how these things are done, right? So 9396 PX, which is the fiber, 2 RU rack unit, 48 ports connected to the front panels. We have 12 port gem module for 40 gigs. Then we have management port dedicated. You have console ports. You have 2 USB ports. You have redundant power supplies at the back. So this is the back view. If you see here, the back view gives you 3 power supplies, 2 power supplies and 3 fan trays. So you have full redundancy across ends. And actually you will see even the airflow, the color coding on the fan trays are different. So if front to back versus back to front, the color coding is done for you. This is 93128TX, which is copper. 3 RU, little bit higher because you're adding another front panel layer. So that's why it becomes a little bit higher. So here you can see that you have 48 ports on this, then you have another ports on this panel. Similar things, you have all the similar features, same as back stuff, nothing different. From the chassis perspective, we reuse it. Only thing that you have to remember, which is important, I actually commonly get these questions from the customers, is I forgot to connect my gem module, I'm trying to boot it up. So it's not going to boot up. So you remember, if you're using fixed leaves or fixed slots of 9300, you need to have gem module also. Because when it boot up, the code looks for this gem module. So you have to have both the chassis and the gem module together. And in ACI, definitely you use as an uplink to a spine connections. So then we go on more on the platform architecture itself, right? So we talked about briefly on the gem modules, 12 port, 40 gig ports, QSFP, gives additional 48 meg buffer because we are using the same ALE engines on it. VXLAN gateway bridging routing capability because we have done the similar headers on this as well. Commonly used for multipurpose ports, right? So we are using with the LED concepts. So actually, you have seen it. What we do, we have a small LED lights. So that actually tells you which port is connected where on this. Redundant power supplies, similar power supplies, but little bit in different fashion. So same as UCS we did for modular chassis, but the form factor because of size is different. We use it in a different way. So port side, as I mentioned, like they're different, like blue or red, it will tell you the speed of the airflow. So how it connects from